Greetings of the day, this is Abdul's Edu Guide, and today we're going to continue the chapter Equilibrium. So let's dive right into it. So we've already discussed what equilibrium is. Equilibrium is, as a recap, I'm just going to share a few points. Equilibrium is basically a balanced condition where in a chemical reaction, the rate of forward reaction will be equal to the rate of backward reaction. So let's look at the type of equilibrium. It's a physical equilibrium, and there is chemical equilibrium. So in physical equilibrium, there is no change to the chemical properties. There is no change in the chemical properties. That is physical equilibrium. The most important examples are the phase transformation processes. That is basically when it changes from solid to liquid, or that's a forward reaction, and liquid to solid in the backward reaction, or liquid to gas, gas to liquid, or solid to gas, gas to solid. In a physical process, there is only change in its physical properties. Here, if we take in solid, if we take ice as an example, and for liquid, we take water as an example, there is no change in the chemical properties. Even in the solid state, it's still H2O, and in the liquid state, it's still H2O. There is only change in the physical properties, that is, when you melt ice, it becomes liquid. And when you freeze it, when you freeze the liquid, it becomes a solid, that is, it changes back to ice. So here melting would be the forward reaction and freezing would be the backward reaction in this case. Same way we can understand liquid to gas by taking water and water vapor as an example. Solid to gas can be understood by taking examples like naphthalene, where it changes directly from solid state to liquid, to a gaseous state. Now let's look at equilibrium in the chemical processes briefly. Earlier we had done the equation. We had done an equation which was N2 nitrogen plus hydrogen, CH2, reversibly gives us ammonia, which is 2NH3. This is called the Haber process. So this is a reversible reaction, and there is a change in its chemical properties, and hence it is a chemical process. Here the forward reaction, as we discussed earlier, would be nitrogen plus hydrogen giving us ammonia, and the backward reaction would be ammonia decomposing to form hydrogen and nitrogen. Now let's look into the physical processes in detail, equilibrium in physical processes in detail. First, let's look into solid-liquid equilibrium. To understand solid-liquid equilibrium, we should take a common example, that is ice to water. Needless to say, ice would be the solid and water would be the liquid. Ice to water. Here the forward reaction would be melting, that is ice changing into water, and the backward reaction would be water freezing to form ice. Now let's understand when it is said to be at equilibrium. So basically, it is said to be at equilibrium in standard pressure, that is at a particular temperature and pressure. The ice and water are in equilibrium if the rate of melting is equal to the rate of freezing. That is ice becoming to water and water becoming to ice are in the same rate. The rate is the same. So we know what is the melting point of ice at standard pressure. It is 0 degrees Celsius. And what is the freezing point of water at standard pressure? It is 0 degrees Celsius. So at this particular temperature, the opposing forces occur simultaneously. Um, Here, ice melting and freezing takes place simultaneously. Both the process occur at the same rate, so the amount of ice and water remains constant. Now let's assume that both of the rate of melting and freezing were not occurring at the same rate. For example, if the temperature was increased to, let's say, 15 degrees Celsius, then the ice would start to melt, right? So obviously, the rate of melting, that is a forward reaction, will be greater than the rate of the backward reaction, which is freezing. So the amount of ice and water will not remain constant. The amount of water will start to increase because the rate of forward reaction is more, which is melting is more. So because it's at equilibrium, the amount of ice and water remains constant. We had studied in the previous lesson, like in the introduction, that at equilibrium, once equilibrium is attained, the concentration remains constant. So that's right. What the forward reaction, backward reactions are. Melting is a forward reaction. And freezing is a backward reaction. Freezing is a backward reaction. Let's read the entire paragraph once more. At a particular temperature and pressure, the ice and water are in equilibrium. That is at 0 degrees Celsius and standard pressure. When it's in standard pressure, the normal melting point or normal freezing point of the substance is the temperature at which the solid phase and liquid phases are equilibrium for any pure substance at atmospheric pressure. When the system at dynamic equilibrium will follow the conditions, both the opposing forces occur simultaneously. Both the process occurs at the same rate, so the amount of ice and water remains constant. Now let's look at the next phase transformation process. Here we have liquid vapor equilibrium, that we can take the example of water to water vapor to understand. The number of water molecules in the gaseous state into the liquid state increases until equilibrium is reached. So let's understand what it says. We know that the boiling point of water is 100 degrees Celsius at standard pressure. So this is when water to water vapor equilibrium is attained. So if you're boiling water, the number of water molecules from the gaseous state into the liquid state, right? So from water vapor to water will increase. That is, since equilibrium is not yet attained, it will keep on increasing. And at the point that equilibrium is attained, we have already learned that when equilibrium is attained, the concentration remains the same. It remains constant. So once equilibrium is attained, the number of water molecules increasing will stop, and the water molecules in the gaseous and the liquid state will remain constant. That is, rate of evaporation will be equal to the rate of condensation. Because here we, like we discussed earlier, if either the rate of evaporation is more or if the rate of condensation is more, then the amount of water and water vapor will change accordingly. So here we know water to water vapor is evaporation and water vapor to water is condensation. So let's assume that if the rate of evaporation was more, then there would be more water vapor than water. There would be more water vapor than water. But if the rate of condensation, that is water vapor changing into water, was more, then the amount of water would be greater. So at the point of equilibrium, at 100 degrees Celsius, the rate of evaporation, rate of condensation is equal. That's what happens at equilibrium. The forward reaction will be equal to the backward reaction. At that point, the amount of water and water vapor will remain constant because the rate of evaporation is equal to the rate of condensation. I hope that was clear. I'll read it again. Liquid to vapor equilibrium. The number of water molecules from the gaseous state into the liquid state increases until equilibrium is reached. That is, rate of evaporation equals to rate of condensation. Great, I hope you all have understood. Now we'll move on to the next phase transformation process. Our next phase transformation process is solid vapor equilibrium. That is from, let's take the example of naphthalene or camphor. When a solid vapor, when solid changes into vapor, it's called sublimation. That is, the forward reaction is sublimation. And when vapor changes into solid, it's called deposition. That is the backward reaction. This equilibrium is attained when, for example, naphthalene balls show sublimation. That there is, it directly changes from solid to a gaseous state. Now we're going to talk about law of mass action for a general reaction of the form A plus B plus C plus D. The small letters represent the stoichiometric coefficient. That is, when we balance an equation, there might be some numbers preceding the compound or the element or whatever. So for example, if we have, let's take the example N2 plus, the same example we have been using for this lesson, N2 plus 3H2 gives 2NH3, reversibly gives 2NH3. So here the 3 would be the stoichiometric coefficient and 2 would be the stoichiometric coefficient. So the law of mass action states that the equilibrium constant or the equilibrium condition is expressed by the equation C. It is the concentration of C raised to its stoichiometric coefficient, D raised to its stoichiometric coefficient. So basically the product of the product of the products C and D, which are each raised to its stoichiometric coefficient, divided by the product of its reactants, which are each raised to its stoichiometric coefficient. So let's understand how this equation is derived. So let's look into how it's derived. So we know that what law of mass action states is that rate of chemical reaction is directly proportional to the product of the active masses of the reactants which is raised to a power of its stoichiometric coefficient in a balanced chemical equation. That's what law of mass action states. That's what we had looked into earlier. So we know that the rate is proportional to the product of active masses of the reactant. Product of active masses means the concentration itself. Right. Now, when we'll consider the equation, which we had seen earlier, that is the general form. When we consider this, we can say that the rate, let me change the pen, rate is directly proportional to A raised to A, B raised to B. That is the product of A raised to A and B raised to B. Okay. Now, what should we do to remove the proportionality sign? The proportionality sign. We'll bring in a constant. So we know R equal to K, which is the constant, and the product of both the reactions. Each raised to its stoichiometric coefficient. I hope the B is clear. It's a B, just to clarify. So now when we consider this equation, let me change colors. Now when we consider this equation itself, the rate of forward reaction, we can say, is equal to Kf, denoting constant for forward reaction, and the product of the reaction. Raised to its stoichiometric coefficient. Product of active masses of the reactants, to be precise. And now we know the rate of backward reaction is equals to Kb, concentration of the product, raised to its stoichiometric coefficient. So we know that when we consider the equation, when we consider the forward reaction, these are the reactants. And the law of mass action states that the rate of a chemical reaction is directly proportional to the product of the active masses of the reactant, which is raised to a power of its stoichiometric coefficient in a balanced chemical equation. So here, that's what we have derived for the forward reaction, that it is raised. We know it's directly proportional, so to remove the proportionality sign, we brought in the constant, and we know it's equal to the product of the active masses, which is raised to a power of the stoichiometric coefficient. Now, if we consider the backward reaction, when we consider the backward reaction, applying the same law, that is, it is directly proportional to product of active mass of the reactants. Here, when we consider the backward reaction, this would be the reactants. So we have rate of backward reaction equals to Kb, which is the constant, and the product of the active masses raised to its coefficient. Now, how did we derive the expression for the law of chemical equilibrium? That is, which we saw earlier. That is the equilibrium constant. How did we derive that expression? So here we know that in equilibrium, the rate of forward reaction is equal to the rate of backward reaction. So from 1 and 2, we can say that both of these will be equal at the point of equilibrium because we have studied that the rate of forward reaction is equal to the rate of backward reaction. So we can say Rf is equal to Rb. Now we have to equate both of them. So when we equate both of them, we'll get Kf by Kb. Since when we equate, we're going to bring the constants to one side, equals to the product of the active masses of the product each raised to its stoichiometric coefficient divided by product of the reactants each raised to its stoichiometric coefficient. Since we know that a constant divided by a constant here, constant divided by a constant will obviously give you a constant. So we get the equation which we had seen earlier, that is Kc equals to so what we've gotten here is the law of chemical, this expression called the law of chemical equilibrium. At a given temperature, the product of the concentration of reaction products, not to confuse between both the term products like multiplication product and the products in the equation, we're going to say reaction product. The product of concentration of the reaction product raised to a power which is equal to its stoichiometric coefficient in the balanced chemical equation divided by the product of concentration of reactants raised to a power which is equal to its stoichiometric coefficient is equal to a constant K. This constant here is called the equilibrium constant. So this is how we derive.